If your models already run on NVIDIA GPUs, how hard is it to move them onto Huawei Ascend 910C or 950 and actually get better performance? In this module, we'll turn that question into a concrete, repeatable engineering workflow you can apply to your own codebase. Ascend isn't just a chip, it's a tightly coupled stack. At the bottom, you have the 910C and 950 NPUs, then drivers and firmware that expose their capabilities. On top of that sits CANN, which provides core neural network kernels, and ACL as the compute language interface. Framework integrations like PyTorch and TensorFlow plug into those layers. All 5 tiers must match inversion. If one layer is out of sync, you'll see missing ops, crashes, or bad performance. That's why Ascend development always begins with checking stack compatibility. When you move a model from NVIDIA GPUs to TPUs or Ascend NPUs, think of it as a pipeline, not a one-off hack. First, get the environment rock solid. Drivers, runtimes, and frameworks correctly installed and visible. Next, port the model by wiring up device placement and replacing GPU-specific APIs with portable ones. Then triage. Find unsupported operations, add fallbacks, or slightly refactor layers. After that, validate. Compare metrics and a few key tensors against your GPU baseline. Finally, optimize with larger batches, mixed precision, and profiling. Before you touch model code, confirm that the Ascend device is actually visible at every layer. Start at the OS. Make sure the PCIe device is detected. If it's not, you're dealing with drivers, firmware, or hardware issues, not PyTorch or TensorFlow problems. Then move up to the framework. List NPU devices, confirm the expected count, and print a device name. Only when both system and framework agree on the hardware should you proceed to porting or performance tuning. When you port PyTorch code from NVIDIA GPUs to Huawei Ascend, device placement is mostly a search and replace job. Anywhere you used CUDA, you'll typically swap to NPU. Selecting the device, setting it, and synchronizing look almost identical, just with a different backend name. The nice part is that your higher-level workflow doesn't change. You still call model, to device, and inputs, to device. So conceptually, you're not learning a new paradigm, you're retargeting the same pattern to new hardware. Moving from NVIDIA GPUs to Ascend also involves a few structural code swaps. First, treat any custom CUDA kernels as a red flag. Prefer high-level PyTorch or TensorFlow ops that Ascend already accelerates. Only if you must, re-implement as Ascend custom ops through CANN. Next, update mixed precision. CUDA AMP calls won't work. Switch to Ascend's AMP APIs like torch npu.amp and revalidate training stability. Finally, remove hard-coded GPU 0 placements. Use device Ascend 0 and proper distribution strategies so your code scales cleanly. When you hit an unregistered Ascend kernel error, treat it as a triage problem, not a dead end. First, ask whether the layer is mathematically substitutable. Many custom activations or normalizations can be rewritten using combinations of standard supported ops without changing model behavior much. If that doesn't work, check whether the issue comes from exotic, dynamic control flow, or shape-changing loops. Simplifying those often lets the compiler generate a valid static graph. Only when the operation is truly critical and non-substitutable should you deliberately route it to a CPU fallback path. On Ascend NPUs, every time the graph falls back to the CPU, you're paying a big latency tax. Data must leave the NPU, cross PCIe, run slowly on the CPU, then come back again. That round trip stalls your high-speed compute, especially in tight training loops or latency-sensitive inference. The rule of thumb is, keep hot paths entirely on the NPU. Reserve CPU fallbacks for one-time initialization, logging, or truly non-critical subgraphs. When profiling, a surprising amount of mystery latency is often just unnecessary CPU detours. Operator Fusion treats several small layers as a single, larger operation that better matches the DaVinci AI core. Instead of launching separate kernels for convolution, batch norm, and maybe an activation, you restructure the model so these stages can be merged. That removes extra memory reads and writes and cuts kernel launch overhead. The key enabler is clean, compatible tensor shapes and standard layer patterns, so the CANN compiler can recognize fusion opportunities automatically, giving you higher throughput with no change in model semantics. Once a model runs on both accelerators, the next step is to validate numerical correctness. Run with fixed seeds and identical inputs on both platforms, then compare the resulting tensors. Don't expect bit-for-bit equality. Different kernels and precisions will introduce tiny floating point drift. Instead, track simple metrics: maximum absolute error, relative error, and cosine similarity between outputs. Define reasonable thresholds based on your task. Most importantly, compare full training or inference curves. If losses and key metrics align over time, your port is numerically sound, even with small per-element differences. When you optimize on any accelerator, treat profiling as a repeatable experiment. Include a warm-up phase and ignore the first few iterations. Compilers, caches, and graphs need time to stabilize. Then measure real-wall clock time per step, or epoch, not just device-reported flops. Break the step time into 3 buckets: CPU input pipeline, memory I/O, and core compute. Fix input and memory bottlenecks first. Slow data loaders or bandwidth saturation. Only then spend time tuning kernels, fusing ops, or changing precision. Migrating from CUDA to Ascend is easiest when you follow a consistent pipeline. First, prepare. Clean up the code, centralize device placement, and make randomness reproducible. Then port, swap CUDA device calls for NPU equivalents, and run the model end-to-end. Next comes triage. When something breaks, assume it's either an unsupported op or a shape or precision mismatch. For unsupported ops, try a drop-in substitute, simplify the pattern, or fall back to CPU. Finally, validate numerically, then optimize for speed.